Okay, so welcome back to another video. So in today's video we have a improper integral that involves the inverse arctangent and the natural log. Specifically, the integrand is the arctangent of x divided by x to the power ln of x plus 1 dx. Actually, today's video is actually going to be really short because this is not a difficult integral to compute. Simply, it's just first thing is that there's also there's a u-substitution involved with the steps, and there's actually going to be also two computations involved that I'm not going to go over the proof over because those two evaluations I actually covered in past videos, which I will link them into the those two videos in the description below for you guys to see the proof, or if you want to try it as an exercise without having to look up these, and feel free to. So just from that, we can actually just get started. So let's start off with our given integral. We'll just call this capital I. So I'm just going to write our given. So this is arctangent x, and then x to the power ln of x plus 1 dx. Okay, so let's perform a u-substitution. Well, I'll just call this t. So we're going to let t equals ln of x. Now I like to solve for x on its own because we have to plug those back in for x for the new variable eventually. So if I just take the exponential to both sides, so we have e to the t is equal to x, then differentiate both sides to get our dx substitution. So that will be e to the power t dt is equal to dx. All right, so now with that, let's actually plug in our let's plug in our substitution and get our new integral. All right, so now we have to put in our new bounds. We have x is equal infinity, so that means for t would have to approach infinity, and then if we have 0, so that would mean t would have to approach negative infinity. All right, so now let's plug everything back in for x. So we have arctan of e to the t, and then divided by, so this will be e to the t and then to the power ln of e to the t plus 1, and then don't forget to plug in your dx substitution, so e to the t dt, right? Okay, this can be simplified out even further, so let's see, the numerators will still remain the same. However, if we simplify what's in the denominator, so we have ln of e to the t, which is just t, and then so now we have e to the t, well, okay, let me put this in parentheses first. Then we have t plus 1, still e to the t dt, right? We keep going further. And now if we actually just combine with the exponent, so this will just be e to the t square, then multiply with e to the t, then e to the t dt with the numerator. So these cancel out. And I'll put this under one, we're just gonna exclude the fraction, just put this under just as a whole, so that way we have this integral of e to the negative t square, then arctan of, what was it, arctan of e to the power t, and then dt. Okay, so let's actually we're going to substitute for our variable t for negative t. So why do we do that? Well, eventually the next steps we're going to get a little creative with it, but the integrals, its area is still going to preserve the same as it's actually just this area, not the area, the graph is actually just going to flip on the y-axis, just taking in inputs of the negative for negative inputs of negative t, but the area still remains the same. So those the two integrals are actually equal to each other. So let's see, if we plug negative t, so e to the negative t, that still stays the same, but then we have the arctan, that will change to a e to the negative t dt. Okay, cool. So that's these two integrals are equal to each other. So now let's actually add the two integrals together. So this means they're both equal to I, so that means double the quantity. So this has become 2 times I. So 2I then equals, let's see, so e to the negative t square arctan of e to the negative t dt. Then I'm just gonna move to the next line. Then add this with same integral, but except this input would be well, how about this? Let me put this as positive t, and then now over here e negative t square arctan of e to the negative t dt. And now we add these two together, so you can just use using the properties of linearity, and I can actually factor out the e to the negative t squared to both sides. Okay, so we have e and then negative t squared, then multiply with arctan of e to the t, and then we add this with arctan of e to the negative t, and then dt. And now we're gonna we know that from this computation that this is actually going to equal pi over 2. And the proof is that, so I actually covered this in a video specifically, I think it's called a trigonometric golden integral, where instead of our inputs for e to the power t, it's just for some standard variable x. If you just follow that same method with the proof, it actually works the same, and then you just substitute e to the power t back onto here. In other words, this is the same thing as 1 over e to the power t, which is the same thing that's from that proof. So if you want to check that out, then I'll leave that link in the description below. The proof follows the same thing, just follow that method, then afterwards just substitute e to the power t into that input, and then you're going to get that the value is actually just still equal to pi over 2. So now that that's equal to pi over 2, so this just 2i is equal to pi over 2, so I'll factor that out of the integral. And then now we have I keep writing that, so this is supposed to be positive infinity to negative infinity of e to the negative t squared dt. But of course we know that, I proved this in a video, this is actually known as the Gaussian integral, and we know that this value is just equal to the square root of pi. And of course I'll leave that I'll leave the video to that computation in the description below for you guys to view. It's actually not that difficult. I also found out from someone told me that you can actually evaluate the Gaussian integral using the gamma function, which I never tried myself, but if you guys want to, feel free to prove that as an exercise and let me know. So okay, so if we do all this, so 2 to the power I, and then just factor this out. I'm just going to change this to in a form of an exponent, so we just add the exponents. So we have 1 plus 1/2, so this is just pi to the power 3 over 2, and then divided by 2. Then all that's left is divide 2 to both sides, so we have that I is equal to pi to the power 3 over 2 divided by 4, like so. And there we have it, the final answer, drawn in the black box, like so. Yeah, not too difficult. I told you the video was short. We got 2 of the proofs that already been proven in past videos that I've done, so the video takes less time in this. So yeah, that's pretty cool if you ask me.